In the last video, we compared two algorithms for finding a value in a list. The first was called sequential search, or sometimes linear search, in which we look at the value in the first box, then the value in the second box, and we keep going until we find the value we want, or we don't find it at all. When we've come to the end, we find that it wasn't there. And we found that the time for that algorithm was proportional to the number of boxes. But we also found that when we use that algorithm in practice, for example, finding a phone number in the phone book, where I have to check every single entry to see, is this the phone number I want? Is this the phone number I want? That if I have 200,000 names and numbers in my telephone book, I need to look at all 200,000. That may take me, I don't know, let's say a few weeks to find that particular number in the phone book. So the point is, sequential search, which sounds like a pretty obvious way of finding something, is actually potentially very slow. We have to look at every entry. On the other hand, if we know something about those entries, so let's say we want to find a name in the phone book, and I know that my phone book is sorted alphabetically by name, then I can use what's called binary search. And in binary search, let's go back to the algorithm. We look at the name in the middle, in the exact middle, and depending on what that name is, if it's not the name we're looking for, so for example, Mike wasn't the Dave I was looking for, we then look in the middle of all of the names where Dave could still be. And since I know that the names are stored alphabetically in this scenario, I know that if Dave appears, then Dave must appear before Mike. Dave must appear in this region, right? And therefore, I look in the middle of the remaining region. And then I rule out another half of the names, and I look in the remaining region that I have not ruled out. I look in the middle of that. So we keep looking in the middle of a region and ruling out half of my collection. And that algorithm is called binary search. And we found that binary search, if used on a phone book, where I know my names are indeed alphabetical, that I can find a particular name very quickly. I claim in about 30 seconds, and you can try that experiment at home. And so we want to know, how is it that it takes only 30 seconds? What is the math behind that leads us to this sense that we can find a name in the phone book much faster than we can find a telephone number? In other words, that binary search is much faster than sequential search. So I want to analyze the running time of binary search in this video. So we're going to make a chart. And in this chart, we're going to keep track of well, let's suppose we're looking for names. Okay, so in the left-hand column, we're going to keep track of, this is going to be, actually, we'll just keep this more general. Size of my list, the size of my collection, the size of my array, the number of elements. In fact, maybe we'll just say number of elements. Okay. And what I want to determine, based on the size of the list, how long. So time to find particular element. And another way of putting that is how many we need to look at. How many elements do we need to look at before we find the one that we're looking for? So let's make this concrete. Suppose I have, in fact, let's make this nice and easy at first. Suppose I have one name in my list. I like to start with easy numbers. 1 is a nice easy number. If I have only one name, meaning I have a telephone book with one person in it, right? This is maybe this is the Vatican, right? There's just one person who lives there, and I want to know, is that person Dave? And all I got to do is compare that one person to the Pope to determine if it's really the one I was looking for. Or alternatively, I have just one box, and I want to know, does that box contain 582? Something like that. If I have just one element in my list, then I need to look at exactly one box. So I need to look at one box, and we'll say that therefore the time is one unit of time, however long it takes me to look at one box. So really, I think this is the number of elements I look at, but I claim that the number of elements I look at has a lot to do with the time for my algorithm. Okay, let's try another one. Let's put a line there so we don't mix these up. We'll just we won't mix them up. We'll be fine. Suppose that I have 3 elements in my list, and I picked the number 3 deliberately here. I skipped 2 because 3 is actually easier to think about. If I have 3 boxes in my list, and I know that my list is sorted. Remember, in order to use binary search, I have to know it's sorted. which box should I look in first? I should look in the middle box. We should look at this one. And once I've looked in that box, how many, and suppose I don't get lucky, and it's not the value I hoped to find, how many other boxes do I need to look at now? Well, just one. I either need to look at this box on the left or this box on the right, but not both of them, right? So that tells me the total number of boxes I need to look at is 2. The one in the middle, plus potentially one on either side. So we'll make a note of that. If there are 3 elements in the list, oops, I want to stick with the same colors. 3 elements in the list, I need to look at 2 boxes. The one in the middle and one on either side. And that's in the worst possible scenario, where I don't find the value until the last box, or maybe I don't find it at all. What if I have 7 boxes? And again, I've picked this number 7. In fact, I have 7 boxes already drawn. Let's go look at that. If I have 7 boxes, I'm going to look in the middle box first, right? And after I decide whether or not that middle box is the one I want, assuming it's not, I can immediately narrow down the places where this value might be from 7 to just 3, right? Either the 3 on the left or the 3 on the right, but I can immediately narrow it down to 3 boxes. So my point is, the number of boxes I need to look at, let's make you dizzy, number of boxes I need to look at when there are 7 boxes in the list, 7 elements, I need to look at 1 element, the one in the middle, plus the number of elements when there are 3 boxes. And if there are 3 boxes, I already know that I only look at 2 of them, right? So I look at the first one I look at narrows down the problem to size 3, and now there are only 2 left. Or there are 3 boxes left, but I only need to look at 2 of them. So 2 more, that's 3 in total. And I think you see what's happening here. When I double the size of the list, and I'm adding 1 to make the math easy, when I double the number of elements in my list, so here I go from 7 to 15, right? Now the very first element I look at, if I look in the middle, I use binary search, based on that middle element, let's do that diagram again, based on that middle element, I can immediately narrow down the problem to either one of these 7 over here, or one of these 7 over here. So that means I need to look at the one in the middle, plus however many you look at when there are 7 boxes left. And I know when there's 7 elements, I have to look at 3 of them. Therefore, I look at 3 over here, plus the one in the middle, in the worst case scenario. And that means 3 plus 1, that's 4. So, how about 5? If I'm going to look at 5 boxes in the worst case, how many elements would there be in the list? Well, the math will be easiest if there are 31 elements in the list. And at this point, you might start to see a pattern. So let's see if we can work out what that pattern is. If I tell you that I look at t elements, and I pick t because the number of elements I look at is the time, right? I'm telling you, when I have 31 elements, I use 5 units of time opening boxes. When there are 15 elements, I use 4 units of time opening boxes. So if I want to open t boxes, how many elements would there have been? What's the formula to go from the number on the right to the number on the left? And if you notice this is roughly doubling, it may have occurred to you that this looks like we're finding 2, right? So 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. So the number on the left is actually 2 to the power of the number on the right minus 1. So 2 to the t minus 1. 2 to the 5th is 32, minus 1 is 31. But of course, that's not the interesting question. The interesting question is, if I know how many elements I have, how long will it take me to find a particular value? Oh, and by the way, I should point out, this is not really true, right? That's true for these lovely numbers that I happen to pick. But what if I picked, 9? If there were 9 elements, then I immediately chop the list into 4 and 4. When there's 4 elements, there is no exact middle. So, and in fact, maybe that's been bothering you, so we should point that out. Suppose there's 10 elements. I'm not going to be able to look at the middle, but I can look at one of the 2 elements that's sort of right next to the middle, right? And if I look at one of those 2 elements, then there will be 4. Let's say I look at the lower of those two elements, the first of those two elements. So there's 4 elements. Let's draw this. I look, the exact middle doesn't correspond to a box, but there's 2 boxes right near the middle. So let's say I look here. Then there are 4 positions to the left and 5 positions to the right. Right? So if I get unlucky, there's now 5 positions left. But we're still sort of chopping the list in half. Just not quite exactly as... the math doesn't work out as pretty. But I claim that our analysis for these perfectly sized lists will actually, when we're done, carry over to imperfectly sized lists like 10, where sometimes we don't get a nice even split because we have an even number of elements along the way. These numbers corresponded to situations where every time we chopped the list, we ended up with an odd number, therefore there was an exact middle, and we ended up with 2 equal-sized parts to the left and right of that exact middle. Alright, but let's keep going with this thought since I'm using up a lot of time here. Suppose I have n elements. Sure, we'll use a different color. N elements. How long does it take me to find a particular element when there are n elements? And in fact, I will leave you with this challenging question to work out on your own, and then in the next video we'll explore the answer. I'll see you there.